For today's question, we're going to solve the question number 6 from chapter 3 of Shigley's mechanical design book, which says, for the beam shown, find the reaction forces at the support and plot the shear force and bending moment diagrams. Label the diagrams properly and provide the values at all key points. So, as we can see in this diagram, we have two kinds of force, which is the concentrated force at point A, which is 500 pound of force, and then we have the distributed force, 40 pound of force per inch, which is distributed along the line from point B to point C. We need to draw the free body diagram, which include the reaction forces. So this is how you draw the free body diagram. So for this free body diagram, we have reaction forces at point O, because at point O, you cannot move this part of the beam because it is locked to the wall. So when it is locked to the wall, it cannot move. So that's reaction forces at here. Reaction forces is basically to counteract the forces that is acting on the other part of the body. For example, at point A, we have forces going downwards, and point B and point C, we have distributed forces that is pointing downwards. So these two forces are pushing the body downwards. So if I don't have these reaction forces, the beam will eventually go down along the wall, which doesn't make sense because we want the beam to stick to this point of the wall. So we need to have reaction forces. Another thing we need to consider is bending. Bending is basically kind of like a rotation for the beam. So as we can see, the forces at A and the distributed forces at point B and C will make the beam bend downwards like this. This is if we don't bend the beam, and this is here when we bend the beam, where we apply load here, kind of like a flexible ruler. So when you apply the forces here, you need to have a reaction moment. So if you see logically, without this bending moment at point O, if we only consider the forces here going downwards, without this over here, the whole thing would rotate until here, which doesn't make sense because we are sticking this beam onto the wall and we don't want it to, for example, do something like this. So that's why we have bending moment at point O. So now we have put the reaction forces of RO and MO at point O. So we're going to solve for this free body diagram. So we're going to assume that going upwards in the direction of Y is positive, and we're gonna sum all of the components of forces in the Y direction, or Y components. So first we see that going upwards, this is Y axis, so RO is going up. So it is positive, and then after that we look at here, we see it's going downwards. 500 pound of force going downwards is negative. Pound of force is negative, and then at point B to point C, we have distributed force of 40 pound force per inch. And in order to solve this, it's quite simple actually. We just need to change it into pound force by multiply the distributed force with the length it is acted upon. So for example, for the distributed force, it acted from B to C. So that length is 6 inch. So we need to have 40 times 6 inch, 40 times 6 inch, so that we get the pound force of the distributed. It makes sense because if you see the unit for the distributed force and the length, if you multiply them together, we get 240, and then this will be cancelled out, and then in the end we get pound force. So in the end, we need to equal this to 0 because it is static, it doesn't move, and RO minus 500 pound force minus 240 pound force equals to 0. So we get reaction forces at O is 740 pound force. So after we have calculated reaction forces at point O, we need to calculate and consider the bending moment of this beam. So what we're going to do is we're going to assume that going counterclockwise is positive, and we need to sum all of the moment at point O equals to 0. As we can see here, the reason we put equals to 0 is that we don't want this to move, and this is a static. And if this is not equals to 0, then whatever forces acting upon this will make the whole body rotate like this. It doesn't make sense because at point O it is attached at the wall. So we need to put it equals to 0 because it doesn't rotate. So at point O, we have the reaction moment MO, which is also acting counterclockwise. So MO. And then we have the reaction forces RO, which we do not consider because it is acting at point O. The moment there is 0. If we go to A, we can see that there is a forces acting downwards. So when the forces acting downwards, for example here, it tries to bend it downwards. So we can see it rotates like this. So when we draw fully, it will be like this, clockwise direction. If it's clockwise direction, it's negative. So negative 500 pound force times, since this is moment, times the length it acted upon from O, 8 inch. As we can see, we have the distributed forces acting from points B to point C. So, and all of them is acting downwards. So we're gonna assume it negative, not assume, it is actually negative. And that we're gonna put 40 pound force per inch times the length it is acting. So 6 inch over here. And then for the distance, in this case, we need to pick the midpoint from B to C. So the midpoint is around here. So it is 3 inches from point B. So we're gonna put the distance of the distributed force from point B to point C with regards to point O. So we're gonna put 8 inches plus 6 inches plus 6 inch divided by 2 because this is the midpoint. So once we have gathered all of this information, we can solve for MO. In the end, we get moment at point O is 8,080 pound of force inch. So once we calculated for the reaction forces RO and MO, we can draw the shear force and bending moment diagram. So first, we're gonna draw for shear force diagram. We're gonna look at point O. So at point O, we only have the reaction forces RO is acting upon it. So 740 pound of force is going upwards. So reaction forces going upwards until 740 is at point O. And then after that, we go to 8 inches towards the right, towards point A. And we have a concentrated force of 500 pound of force going downwards from 740. Going downwards is at this level. And in order to calculate that, we just need to minus 740 minus 500 is 240. So here is 240. After point A, we're gonna go to the right 6 inches towards point B. So at point B, it is the start of the distributed forces acting downwards. So when we have distributed forces, the way you're going to draw in shear force diagram is it is not a straight line, but it is more to a slope, a linear slope. So if you can see, from point B to C, all of the arrows is going downwards. So from 240 over here, it will eventually decrease to 0 because 240 going upwards, positive, and then you gradually put load going downwards until 0 at point C. So that is why at point B, you have load that is 240 and then going to a straight line towards 0 at point C. So once we draw for the shear force diagram, we're gonna now draw for bending moment diagram. The way we draw it is by separating it into parts. So for part OA, which is, if we do here, from 0 up until 8 inches. So if you can see from here until here, we're gonna do M1 would be equals to negative 8080. So we're gonna consider the existing moment located at point O, which is here, the reaction moment. And then we're gonna consider, since this is part OA, here and here, so we need to consider the reaction forces of here. So positive 740 times x. When x equals to 0, which is at point O, we get M1 equals to negative 8080 pound force inch. So we can get over here negative 8080 pound force inch. And then after that, we can calculate for at point A, which is when x equals to 8, which is M1 equals to negative 8080 plus 740 times 8, which is negative 2160 pound force inch. So after that, we're gonna go to part A to part B. So part A to B, which is from 0 up until 6. So at here it is 0, and then until here it is 6. M2 is equals to negative 8080 plus 740 times x plus the previous length, which is 8 inches, plus negative 500 times x. When x is equals to 0, which is at point A, M2 would be negative 2160 pound of force inch, which is the same as here. So here is still the same value. And then now we're gonna go to point B, which is when x is equals to 6. So M2 would be which is negative 720 pound force inch. So we can see here that is negative 720 pound force inch, which is here. At point B, it is here. So you're gonna draw a straight line here, here, and then after that, you're gonna draw another straight line here. Part BC, which is from 0 until yet another one, 6. So here's 0, here's 6. So 0 is like at point B, 6 inches is at point C. So at this part, we're gonna do it like this. So M3 is equals to negative 8080 plus 740, x plus 8 plus 6, 8 plus 6 because we consider the length before this part. So after that, plus negative 500, and then x plus 6, negative 40 pound of force times the length it is acted upon. So the length is here to here, which is now a variable since we put this a variable. After that, we put another one x, and then we divide by 2 since we only consider the midpoint. So now we're going to calculate for this. When x is equals to 0, m3 would equal to, if you calculate this whole value, when you substitute x equals to 0, you would get negative 720 pound force inch. And then after that, we go to point C, which is at x is equals to 6. We would get m3 equals to 0. So from here is a straight line, another straight line, and then another straight line until 0. 700, negative 720 and negative 720 here for part A, B, and BC is the same. A, B, and BC here is the same. So in the end, this is how you draw the bending moment diagram. So this is the overview for the solution for question number 6, and here are the highlighted answers so that you can check.